So what I have here is a TXRX Systems cavity filter. This one is a quarter wave VHF tuned filter. I'm not 100% sure what frequency this is tuned into, and we'll find out in this video. But what I'm hoping to use this for is in a APRS, digipeater, N0AGI, and iGATE sort of an operation. So I'm hoping to tune this to 144.39 and use this in the front end of a forthcoming digipeater or an iGATE. As you might know, the band pass for an APRS sort of an operation needs to be quite narrow. The wider it is, it passes through quite a bit of noise into the system, and we want to avoid that. And the best way to tackle the noise is to keep the band pass bandwidth very narrow, so that it only passes through the frequencies that we are interested in. So given this is a 144.39, we can be very surgical about how much of that bandwidth we want to allow versus reject, if you will. So whatever we do with the band pass, our goal should be to keep the band pass bandwidth to be quite narrow. So that's what I'm hoping to accomplish here. I think as such we all can agree that the APRS frequency is fairly noisy, saturated, and flooded with digipeaters and the stations that are transmitting their location or their telemetry data into the air. There's also quite a bit of spurious emissions coming into that. So if your station is receiving these packets is exposed to that noise, I think the performance of a digipeater and the iGATE is definitely inhibited because of that. So my goal is to see if we can tune this such that our band pass bandwidth is narrow and we are only allowing what we really care about and discarding everything else. I'm even thinking our bandwidth should be no more than maybe 100 kilohertz or maybe lesser. I don't know. TXRX Systems makes high quality filters, and I have no affiliation to them, by the way. And I came to this filter through a purchase on eBay, and I went to their TXRX Systems website and I did some research on this type of a filter. And they have some pretty good video on YouTube, and I'll put a link to that in the description below. And they kind of speak to some of the key components of the filter, what is all involved in tuning a filter such as this one. So here's a top view of the cavity filter. It's made of a few parts, and I'll quickly walk through those. The first one is this larger coarse tuning rod, or quote-unquote plunger. This is meant for attaining coarser tuning of your frequency, your resonant frequency that you want to set for this cavity filter. There's also a finer tuning rod or tuning plunger in the back, and that is meant for fine-tuning your frequency, your resonant frequency. The larger tuning rod is held together by this set screw, a hex nut, sort of a set screw that you would loosen up to set free this plunger, and then you would move this plunger in and out to attain the resonant frequency. And once you attain that frequency, you would lock it in place through this hex nut. And the one in the back is used for finer tuning of the frequency. It is held together by the circular lock nut, and then of course you would loosen that up, and then again you would push this in and out to attain a finer tuning. And once you attain that, you would lock it in place by that circular lock nut. On either side of the tuning rods, we have the input port and the output port. The input port is obviously is meant for the source for your frequency, and then the output port is made up of two ports. I don't know if you can see it. There are two ports to that output port. In a typical duplexer combiner, sort of a real life scenario, you would have multiple of these cavities working together in harmony to be able to do band pass, band reject, and whatnot. So there's a scenario where the second port on the output side is connected up to a following cavity filter through a T-junction. Of course, in our case, we won't have a need for a T-junction. We want this filter to act as a band pass filter. Therefore, I have capped out the second port with a 50 ohm dummy load. And then the first port on the output side is then connected up to my spectrum analyzer. So the input on the cavity filter is fed by the output coming in from my spectrum analyzer's tracking generator. And I'll show that to you in a short while here. And then the output from the filter is connected up to my input, RF input on the spectrum analyzer. And we'll cover that shortly here. So that's a quick view of the top section of the cavity filter. So because I only have one camera, I won't be able to show you the tuning operation and the visual on the spectrum analyzer. So I'm going to switch the camera to the spectrum analyzer and know that I'll be working on both the coarse tuning plunger and the fine tuning plunger as we work through the tuning process. So here's a view of the spectrum analyzer. Before we zoom into the visual a little bit, this is the tracking generator's output that feeds the filter's input port, and this is the spectrum analyzer's RF input going into the spectrum analyzer, which is fed by the filter's output port. So with that, let's zoom in a little bit. Okay, first things first. We know for sure that our filter is a VHF tuned filter, but we don't know exactly what it is tuned into right now. And we need to first figure out whether it is closer to 144.39 or how far it is from 144.39, so that we can then make a decision whether we want to use the coarse tuning plunger or the fine tuning plunger, depending on how far or close we are to our target frequency. So because we don't know where it is tuned right now, what I have done is I've set my start frequency to 100 megahertz and my stop frequency to 200 megahertz, about 100 megahertz of bandwidth. because we know that this is a VHF filter. So what I'm going to do now is I'm going to turn on the tracking generator. Let's go into the auxiliary control, and let's go into the tracking generator. The tracking generator, just to do a quick level set, I have set it up to operate with a negative 10 dBm source power. And just for safety reasons, I set it to that level and operate from there, knowing that there's a negative 10 dBm insertion loss offset in our process here. So once we have confirmed that, I'm going to turn on the tracking generator. So we are noticing a couple of things. One, we are seeing that the filter is in fact tuned to some frequency within that 100 to 200 megahertz bandwidth, and we see that. We need to figure out what that is. So let's go to peak search. And within peak search, we are looking at that it is tuned to about 128.0 megahertz, which is a good sign. And I'm also noticing that the peak and the band pass bandwidth is quite narrow, at least from where we are looking at. Without zooming in too close, at least at a high level, we can tell that the bandwidth is quite narrow, which is a good sign for us. It's exactly what we need for our bandpass operation for APRS frequency. Of course, we need to go further deep into that peak and determine exactly what the frequency is or exactly what the bandwidth is, etc., which we will do once we get closer to the target frequency of ours, which is the 144.39. But for now, all I care about in this step is to determine approximately how far we are to the 144.39. It looks like we are quite a bit a ways, and that there is about negative 5 dBm insertion loss at that frequency, at that zoom level. So that's all I care about, at least for now. But once we get closer to 144.39, we will need to zoom in further and make sure our bandwidth is narrow, our dBm loss is not too crazy low, and so on and so forth. What this tells me is that I will need to use my Coarse tuning rod to move this resonant frequency to where the 144.39 would land. So our next step would be to move this marker to where the 144.39 would land. So I'm going to go to my marker and I'm going to say 144.39 megahertz. So that is the 144.39, but I want to move that to the center frequency. So I'm going to go to marker to center frequency. So right now, this marker is located exactly where 144.39 would be, and that is moved to the center of your visual. This is where our filter is currently tuned to. Our job would be to move this resonance to 144.39. So what I'm going to do off camera is I'm going to work on the Coarse tuning rod, and would be pushing the tuning rod in and out so that we could move this resonance closer to 144.39. And once we get closer, we will need to further tweak it so that it is exactly on 144.39, and also determine the bandwidth for the band pass, etc., etc. But let's get the first step done to moving the resonance closer to 144.39. So I'm gonna loosen the hex nut on the coarse tuning rod, and now I'm gonna pull the plunger outward, and as I do that, you will notice the resonance navigates or travels through that frequency range and gets closer to that marker. So right now that marker is at 144.5 megahertz, and now I believe we are closer to where we want to be. We're a little bit off, about 0.2 or 0.1.1 or whatever kilohertz. So let's zoom into this peak a little bit. And to do that, let's go to span. Our current span is 100 megahertz. I'm trying to see if I can get a better focus on this. All right, our current span is 100 megahertz. I'm going to change that to, let's say, 10 megahertz. That brings us closer to that peak. As you can tell, we're still a little bit, the peak is a little bit toward the left, so we need to push that a little further to the right. So I'm going to pull that coarse a little bit more. I'm going to go back to my marker. We're about 144.50. I'm going to change the span to even further. I'm going to change it to 5 megahertz. And let's see where our marker is. Marker function tracking on. Let's track it now. Let's go back to the marker. And we're a little ways off, a little bit off rather. I think that's how much I can go with the coarse tuning rod. I'm gonna lock that hex nut in place and then start to work on the fine tuning rod. So my coarse tuning rod is set for now. We are very close. We are at 144.375 or 388. So I'm going to loosen the lock nut on the fine tuning rod, and I'm going to push it in and out and see what we can do there. I'm going to push it in a little. I need to push it in rather than pulling it. We are a little too a ways now. I'm going to change my span to even closer to 1 megahertz marker. 144.413, that's we're getting closer. A little bit outward. There we go. Need to move it a tad bit out. We're so close, yet so far away. I will call that done. We are at, it's fluctuating between 393, 390, 388, but I think we need to, I'm going to see if I can tighten this. No, I think, you know what, let's go a little. I'm going to call that done. We are at our target. Close enough. That's, well, that bothers me still. So let me see if I can go any better. I'm going to call that done. We are very close to our target. It's fluctuating between .390, 393, 395. That's good enough. So this is fantastic. So I'm now locking the finer tuning rod in place with the lock nut, and we will call that done for our frequency tuning. So our next step would be to zoom back out and then do some confirmation of how this filter is performing using my signal generator, the Rohde-Schwarz signal generator, the SME03. We'll put out the 144.39 frequency, and then we'll see how the harmonics show up on this filter, and how it behaves and its frequency response, and its capability to filter down primary, secondary, and tertiary harmonics. And let's take a quick look at that. So let me switch the camera, and let's dive right into it as our next step. So over here, this is my Rohde-Schwarz SME03 frequency generator that you may have seen in my previous videos. So what I've done here is I've set it up to put out a 144.39 frequency at 10 dBm source power. And our goal is to see how our filter responds to this frequency, and how our filter performs and responds to the harmonics, just for us to confirm how this would behave. What I'd like to do first, before we even connect our filter up to the signal generator and to the spectrum analyzer, I want to quickly show you the harmonics without the filter on the spectrum analyzer connected up to my signal generator. So completely bypassing the filter, connecting the signal generator directly to the spectrum analyzer. Okay, so what we have here is the harmonics that's presented to us in response to the signal generator's input on the spectrum analyzer's RF input. So what you're seeing here, the highest peak, that's our frequency, the 144.39. And then this would be our secondary frequency, which is the delta between these two peaks is about 144.39 megahertz. And likewise, the distance between this secondary and the tertiary should also be around 144.39 megahertz. So this response is without our filter. Our goal is to see how this responds with the filter in line, and determine whether our filter is working as planned. If our filter works as planned, the secondary and the tertiary frequencies should be completely subdued or discarded or rejected, if you will. So we need to confirm that. But before we go there, take a note of our bandwidth. We are at start of 100 megahertz and a stop of 600 megahertz. So that's quite a bit of a bandwidth. With the larger the bandwidth, we lose the resolution of these peaks. So if I were to do a peak search, that is our first marker, that is our frequency. However, the readout shows that it is 143.8 megahertz. But rest assured that, that is our 144.39 frequency. But because we are losing the resolution, because we are zoomed out so far out, the markers are not able to give us that granular detail of those peaks. But just rest assured that those are in fact accurately located. So what I'm going to do here, before we switch and put in our filter in line, I want to show some additional markers here. I'm going to go back to my marker. I'm going to turn on my marker 2, turn that on, and move that to the secondary harmonic. And the secondary harmonic is also about 288.8 megahertz. And let's go back to our marker, turn on the marker number 3, turn that on, and move it to the tertiary frequency. I'm going to go back to my marker function, turn on the marker table, so we can see all of these 3 markers in action. Again, ignore the fact that they are showing, the first harmonic is showing at 143.8. In reality, that is our 144.39 or so frequency. And notice that each of these frequencies is about the 144.39 megahertz apart. Okay. And notice that the dBm is negative 10.30, meaning given the source is negative 10 dBm, at that zoomed out level, it is showing we are about 0.2 dBm loss. Again, that is not accurate, because once you start zooming in, you will get the better accurate picture of how much of insertion loss we are experiencing here. Again, that's not the intent of this video. Our intent is to make sure that our filter is performing in its bandpass behavior, and how much of these secondary and tertiary harmonics it's able to subdue or reject, quote unquote reject. All right, so let me insert the filter in line and see how this performs. Okay, so what I have here is I've inserted the filter into our test scenario. The output from this tracking or signal generator is fed into the input port in here, and the output from our filter is fed into the spectrum analyzer's RF input. So right now, our device under test, this filter, is in line with our test scenario. So now that our filter is in line with our test scenario, As you can tell, the primary harmonic, which is our 144.39, is retained. However, the secondary and the tertiary harmonics are completely subdued or quote-unquote rejected, which is exactly what we'd like to see in our scenario. One thing I would call out, also in our marker table, the secondary and tertiary harmonics insertion loss are completely at the floor at a negative 65 and 64-ish dBm. Again, these dBm values are not truly accurate, but we're getting a ballpark estimate that the filter is in fact working as designed. We have been able to successfully keep our 144.39 and yet quote-unquote reject everything else that falls outside of our narrow band frequency within that band pass filter. So that's number one. Number two, if in case you're looking at using this idea in your APRS digipeater or an iGATE scenario, I would urge that you use the right type of cables for your filter and make sure that you are paying close attention to the insertion loss, because once you start using better cables, your insertion loss would improve. So in your experiments, I would urge that you use the right cables for your experiments and also get your insertion loss to minimal loss as much as you can. So with that, thank you so much for watching. I hope this was useful and intriguing. I'm definitely planning on using this idea in my forthcoming APRS digipeater or an iGATE operation in the future. Thanks again, and we'll talk soon, and God bless.